So you travel back in time and you meet Isaac Newton, and you're like, Newton, bro, like you're the father of calculus and modern science as we know it, but like your calculus notation is just so bad. I mean, look at Leibniz's notation. You can see that it's the relationship of the rate of change. You can tell what the independent variable is. That's x. Same for Lagrange's. Plus, it's easier to read. Yours is like y dots. It's so hard to see, and you can't even tell what the independent variable is. All you see is that y. It's like, where's the x? And Newton's like, that's absurd, and you're absurd, and you're like, nobody calls me absurd. So you enter into a bet, and you're like, you know what? If I win this bet, you have to rename your famous unit Newtons into bananas. And Newton doesn't know what bananas are, but he's like, okay. And so the challenge is to find the derivative of x to the 10, and you have a hidden advantage because you brought a calculator, and Newton's like, oh my god, what is this magic even? So you're like, alright, I totally got this. I'm just going to find the limit of x plus h to the 10 minus x to the 10, all divided by h, and you start expanding. It's like x plus h, x plus h, x plus h, blah, 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 blah. And then Newton's like, he's done already. And you're like, what? That doesn't make any sense, and you've dishonored yourself, and you feel like you could cry until you realize that you have a time machine and you can just start all over after you've learned. So fear not, it is totally possible to defeat Newton at his own game because it is very easy to find the derivative of a function when that function takes the form x to the n, and that's called the power rule. So let's begin. Recall that the derivative of a function is just given by the limit as h approaches 0 of the function at x plus h minus f at x all over x plus h minus x. So that's just the difference in the y values over the difference in the x values. And of course the bottom just simplifies out to h because x and negative x cancel out. So if we have f at x is equal to x to the n, well, the derivative is just going to be the limit as h approaches 0 of x plus h all to the n minus x to the n. So just applying the function here. And, there's a problem that appears here because as you increase the power n, the expansion x plus h to the n becomes incredibly difficult to calculate. In fact, well, let's just move that slider up to 100 and you can see like this isn't something that you're going to be able to achieve in like one of your lifetimes or something. So, what's the solution to this? Well, let's look at a simpler example. Let's just say that the power is 3. Okay, so we've got a nice 4-term expansion here. And note how when we put this into our limit thing, the x to the 3 terms cancel out because, well, you've got your x to the 3 as the last term of that expansion, and you got a minus x to the 3. Okay, so what do we usually do next? Well, we have to cancel out the h from both the numerator and the denominator. So we're just going to go through and reduce the powers of h by 1 for all of these terms, and that way we can set h equals 0 and evaluate the limit. Previously we couldn't do that because that would have given us a 0 denominator and it would have been undefined. So we set h to 0 and then all the terms go away except for one, 3x squared. Well, where did it come from? Well, it came from back here. So it was the term that it contained exactly one h. And in fact, that's the only term that matters because, well, the last term, x to the 3, is cancelled out by the negative x to the 3 later on, and everything else just gets set to 0 when h is set to 0. The term that contains exactly one h gets the h divided out, and therefore doesn't get affected later when the h is set to 0 because it doesn't have an h in it later on. So it becomes the only term left over, and it is the one that gives the derivative. So let's look at the pattern of the terms that only contain one h. So for the power of 1, it's just going to be h. For the power of 2, it's 2hx. For the power of 3, it's 3hx squared. For the power of 4, it is 4hx to the 3. So it's just the second last term for all of those for anyone looking up there. And if you see the pattern here, well, the one h term can just be described as n times h times x to the n minus 1. So where n is the power of the original function. So for example, in the power of 4, it's just 4hx and then 4 minus 1, which is 3. So we have like a general rule here. The h there gets divided out because that's part of our process of finding the limit, right? We cancel out the h with the denominator, and that just leaves n times x to the n minus 1. So we get this general rule. We get the derivative of a function x to the n is always going to be equal to n times x to the n minus 1. And if you want to look at an example of this, let's take the example of your bet with Newton. Well, the derivative of x to the 10 is going to be you move that 10 to the front, you subtract the power by 1, and it's going to be 10x to the 9. And now you can go tell all your friends that their unit of acceleration is now in bananas and not newtons. Cheers.